All right, welcome back. So we've spent a while talking about public key cryptography in the context of encryption. So you have your two keys. I'm trying to communicate with somebody, or I want someone to communicate with me. I give them a public key. I keep the private key. You can see this little diagram here. I have a message. Let's say Kevin encrypts it using the public key, sends it to me, and I'm the only one who can decrypt it with the private key. That's a traditional use of cryptography, communicating and trying to obfuscate or hide a message and then being able to decode or decrypt that message on the other side.
Yeah, that's the one that Caesar was trying to do.
Yes. Now we're going to flip it on its head and show you, basically, if you switch the order of the keys, you can do something totally different. And the reason that we're showing you this, it's called private key signing, is that it's what Bitcoin uses. Bitcoin doesn't actually use public key cryptography to encrypt anything. This slide doesn't exist in the Bitcoin world. It only works, or it only takes advantage of the other direction. And it's kind of a big pivot here, and it might be a little jarring, but bear with us. We're going to devote a good amount of time to explaining how this works, because it's kind of unintuitive that you would want to do this in the opposite order, but we'll explain why in just a second.
All right, so let's review our equations here. This is how one would encrypt a message using a public key and then decrypt it with a private key. You take your message, you raise it to the public key, which is just a number, modulus n, which I think we called m in a previous chapter, should be n. That will give you your ciphertext, your encrypted message. And then you pass your encrypted message over even an unsecure line to your destination, and only they will be able to decrypt it with their private key. So we've compressed this down into one line. We've sort of simplified the equation that if you just take the message to the public, mod n, you take that result to the private, mod n, you just get message. This is both of the equations on the previous page mushed into two lines. Now, if we keep extending that out, you can take the result to the public, mod n, to the private, mod n, and ultimately you're going to get the same message out. There's no reason you'd really want to do this over and over, but we just want to show you this because this is a process that you can repeat over and over. This is called idempotence.
What was that?
Idempotence, idempotency. This means that you can repeat the operation over and over and you're going to get the same result.
So this equation here would just simplify down to the original one we saw, this. Or we could, if we could have 6 pairs, blue and then orange, but public then private, and it would simplify down to just this again.
Yeah. As long as they match, and as long as they're paired, then you're going to get the same message out ad infinitum.
So why are we showing you this?
Because you can switch the order. If you take the message, raise it to the private key, mod n, and then to the public key, mod n, you still get the message out. This process, the fact that you can switch the two, actually has a really interesting application in terms of cryptography. And that's what Bitcoin is going to use, hint, hint, and we're going to explain that in the next video. But side by side, what we just want to demonstrate here is that the order in which you apply these, as long as they are paired, is going to still give you the same message output.
Yeah.
That relationship between private and public key applies regardless of the order that you apply them in.
Yeah, and it seems weird, right? Because if you have a public and a private key, you should be the only person who knows the private key, and we've been talking about you use that to decrypt a message that someone sends you. Why would you ever want to encrypt a message with your private key and then send it out so that everybody could decrypt it with a public key? What use is there for that? That's what we're going to cover in the next video. We just want to demonstrate right now that mathematically it works just fine. It's totally possible.
So what we're about to cover in the next video is called a digital signature. The idea of signing with your private and then letting people verify that with your public key.
All right, welcome back. So in the last video, we talked about how we could use a private key to encrypt something, and then anybody with a public key could decrypt it. But that makes no sense as far as like sending a secret message. Why would you want to send a secret message then that everybody could decrypt? It's not really a secret anymore. So what's the use case of doing this? What's the utility?
So it has to do with proving identity. And this is our clip art representation of something called a private key sign, something often called a digital signature. And this is the digital equivalent of signing a document. In the same way that when you sign a check, the thinking is that only you could produce your handwritten signature.
Which very faulty logic. It's so easy to just copy a signature. That's not the case with digital signatures.
Digital signatures are much, much, much more secure than a handwritten signature. So the thinking here is that when you create a key pair, only the owner of the key pair, somebody who possesses knowledge of the private key, could create a valid digital signature. And when we say valid digital signature, we just mean that when it's checked against the public key, that it reports it back as correct.
First, let's just prove the math that it still works going this direction. So we had the opposite of this slide. Our key pair we've been working with, a very simple one, 23 and 7. So if we used 7, like we did a couple videos ago, to encrypt, and then we could use 23 to decrypt, it worked. We can go the other direction though, and remember the math. Let's say our message is the number 16, a very simple message. If I take 16 and I raise it to the 23rd power, mod 55. So I'm using Wolfram Alpha just to make this a little easier. So 16 to the 23rd gives us this massive number. And then I'm going to just mod 55, was it?
Yep. So your output is 26, and that is Colt's digital signature. Now what we're going to do is we're going to verify that 26 against the public key by raising 26.
And what was the public key?
It was 7.
All right, so we do 26
to the 7th
to
power.
the 7th power, and we can do this all at once too, but that's the number. And then we do
we're gonna do mod 55. And our output should be 16. 16 there, the original.
Okay, so the math works going the other direction.
Yeah, and it looks the same way that encrypt does, where encrypt, you raise it to the public key, and then you mod M, you raise it to the private key, mod M, and then you get the original value back. So now how would this be useful? How would someone use this in a digital context? Well, digital signatures are used to create a signature of an important document that one needs to demonstrate they actually created. The thinking is, if I actually sign a contract in real life, my signature is proof, or is proof enough that I was present and I gave my permission. I signed the document.
Yeah, I like to think of it as the private key is what gives you power in either direction. So if you're talking about encrypting something, and we're talking about communicating across enemy lines, anybody can send me a message with a private or with a public key. I'm the only person who can decrypt it. But going the other way, the power that I have is that I'm the only person who can encrypt something with my private key, such that the public key will actually make sense of it, that people can prove that it was me. So it's not about securing a message or hiding anything. It's purely about saying that I'm who I say I am. I have the private key. That's literally all it means. It's just about proving identity. So if I wanted to send Kevin this document, a really important document,
important.pdf,
and I want to make sure that when he gets it, he knows it was from me, or at least from my computer.
Yeah, I don't want Colt's evil twin brother to create a second copy of important.pdf with different details and somehow different content. I don't want to mistake that for the real thing. I want Colt's proof that he was the one who created it.
Yep. So I have a key pair that I've generated, a much, much longer one compared to 23 and 7, but the same relationship, really large key pair. And I use my private key, and I tell everybody else the public key, and I say, hey, you can use this public key to prove that I sent something to you. But first, I sign it with my private key, which is it's the same as encrypting. We raise it up to the power. We'll talk about exactly what we do, but just for now, we take this document and we sign it with my private key. I'm the only one who has it, and that generates this signature, which apparently my signature is Picasso's signature.
Looks just like Picasso's signature.
So then Kevin gets that document and he gets the signature, because remember, we're not trying to hide the document. This is all out in the open.
You would send your document in plain text alongside it. This isn't about hiding it.
No, it's just about proving that it was from me. So then Kevin takes that signature and he has that public key that I sent out to everybody, or maybe not everybody, but he has it along with anybody who needs it. So he can use the public key to then verify that I am the one who actually encrypted this, who used my private key.
Now, suppose that Colt's evil twin brother has a signature that looks a lot more like John Hancock's. If he were to sign an evil copy of the document, and I were to use that signature and plug it in to Colt's public key, then the output would be, it would reject. It would be it would come up as an invalid signature.
Yeah, it wouldn't match. Just like the other direction. If we have a mismatch between a private and public key that aren't a valid pair, if Kevin encrypted a message with a public key, but then someone tries to use the wrong private key, they're not going to be able to make any sense of it. It's not going to work. Going the other direction is the same thing. It's the same relationship. It's just a different application.
So it really comes down to, I look up Colt's public key to determine, and then I plug in his signature to determine if he really created the document. And that's another way of saying, I look up his public key, plug in the signature to determine whether or not Colt had the secret key.
And if you miss that, it's a really small change. Just this little text here.
Yeah, and we're calling it secret key, private key, synonymous. Now, a minor detail for implementation's sake. This isn't really important to the end user, but if you're curious, when you're actually signing a document, you're not going to actually raise an entire PDF to an exponent. A PDF, if you were to think of it as a sequence of bits and bytes, that's a massive number. And then if you want to raise that to another massive number, it's going to be prohibitively slow. Instead of Colt actually signing the entire document, what he instead signs is he signs a fingerprint of the document. And the thinking is that if his evil twin were to also be trying to interfere with this, the evil twin would, one, not be able to generate a document that had the same fingerprint, and two, would not be able to digitally sign it. So both of those steps would be too difficult for somebody to spoof.
So the math ends up looking like this, where we have the fingerprint that we're signing, and then we're taking that result, and then we're using the public key to check or to verify that we get the fingerprint back.
Now in review, here are the two ways that you can use a public-private key pair. On top is encryption, which we covered in the previous videos, where you take a message, you raise it to the public key, or you somehow use a public key to encrypt it, and then you use the private key to decrypt it. With the signature, what you instead do is you use the original message, you sign it with the private key, which produces a signature, and then you send the signature alongside the message to your destination, and the destination, the recipient, will then use the public key to verify the output. And more accurately, what you're doing is you're actually fingerprinting it and then sending it.
Here's the same thing with somebody who doesn't have the private key, my evil twin, allegedly. So they would try and sign it with some private key that doesn't match the public key that everyone has. Because remember, it all hinges on the fact that I, ahead of time, say, hey, this is my public key, everybody, this is how you know it's me. So Kevin is going to use this public key, and it's expecting the exact corresponding private key to be what signed the document. So if it's some random other private key, whether it's totally random or just a wrong private key, the signature is totally different, and so my public key won't work. And then Kevin knows that somebody did something along the way, or that this didn't come from me.
Yeah, so I would just trust the first document, the top document.
And then remember, it's fingerprints that we're actually signing rather than the entire document.
And note that the actual fingerprints that are ultimately signed, if Colt's evil twin has a different document, it will have a different fingerprint. So not only is the private key different for Colt's evil twin, the fingerprint that Colt's evil twin would be using would be totally different.
Mm-hmm. So in summary, the question that we're trying to answer here by going the other direction, using the private key first and then the public key, is to check if the generator of the key pair, the owner, the person who has the private key, did they create this file or this message? And the way we do that is just by using the public key to verify.
Now you might notice a similarity between fingerprints like SHA-256 and Ketchak and digital signatures. Now, both of them do accomplish one thing in the same way. They prove that a document has not been altered. You can use a digital signature in the same way that you use SHA-256. But digital signatures are, one, slower, and two, have an added benefit. And digital signature doesn't just demonstrate that something hasn't been tampered with. It also demonstrates that it was created by the same person that owns a public key, or that created a public key. So it's not just integrity, it's authenticity.
Okay, welcome back. So now we get to the big moment of putting together Bitcoin and public key cryptography. We talked about encrypting things, the top part here, which Bitcoin doesn't actually do. But then we talked about is it the inverse? The opposite?
The opposite? Yeah, I think the opposite.
We talked about the opposite way, where you can use a private key to sign something to prove that it was you signing it, and someone uses the corresponding public key to verify that. Same keys, just different order. So this is what relates to Bitcoin, and that's what we're going to talk about in this video, is how it relates. When are things signed? When do you use a private key to sign something? Before we go any further, let's revisit Billy, Kilgore, and Montana. These are our three hypothetical people in our super small network, we're just going to work with transactions between the three of them. So each one, we've color coded them. They each have an address, which, remember, the address is based off of the public key. They're not quite the same thing.
So technically, these addresses are the SHA hashes of public keys. You don't really need to know that, but for the detail-oriented, we just wanted to clear that up.
Okay, so everyone has an address and the corresponding private key. Okay.
So we show here that Montana receives Bitcoin at her public key, at her address. And now here's the big leap we're going to take. And this is that Montana can unlock the Bitcoin that she has received at her public key, at her address, with the corresponding private key. Now, what does that look like? So Montana will take the address, and in order to move Bitcoin from that address, she will produce a signature using that address's private key. Now remember that the address is public information. It's a public key. And Montana's private key, generated at the same time alongside the address, has been kept hidden all along. When Montana wants to spend the Bitcoin associated with her public key, she will prove to the network that she is the real owner of that public key by creating a signature that only she can create.
Right. Well, otherwise, anybody could see that, oh, this address, whoever owns it, has 10 Bitcoin in it. Why don't I just make a transaction from that address to myself, for example, or to some person I owe money to? The only thing standing in the way of that is that Montana has to produce the valid signature, has to basically use the private key that she's been keeping secret this whole time, or her wallet app has been holding on to prove that she actually owns it. Otherwise, in this transparent system where everyone can see all the balances of any address, anyone could just spend stuff all over the place.
Yeah, Colt could not generate a valid signature based on that address. He can only generate signatures based on addresses that he has generated.
Yes, unless maybe I could kidnap Montana and torture her, and then force her to show me her phone, and then I could go into her phone and find the private key.
So yeah, under duress, people can steal your keys, but in general, the math, it's bulletproof.
Yes, also, yeah, I don't believe in
people are
torture.
Fallible, and yeah, we don't condone torture for keys.
Okay.
So in terms of our analogy, we need to update you. We have left out, and for simplicity's sake, we didn't include what was inside of this clip art envelope. Inside of this envelope, this Dropbox where we have stored Bitcoin, where did that Bitcoin come from? Well, that Bitcoin came from another address. And how did it move from the other address to this envelope? How did it move into the Dropbox? So the owner created a signature using the private key corresponding to that address, which told the Bitcoin network, or showed the Bitcoin network, hey, I have permission to move this Bitcoin.
Okay, so let's walk through a little bit of an example.
So here we start with Billy, and we're not going to talk about how he got this Bitcoin, but pretend he has it in an address. He owns the address. He owns the private key.
Well, let's say he mined it.
He mined it. That's perfect. Yeah.
So there is no from address. So this is his address, Billy's address that has 3 Bitcoin. And what he's going to do is send all 3 Bitcoin to Kilgore.
Yeah. So Billy is going to generate a signature using the private key corresponding to that public key.
Yeah, so if we actually step back here, at this point, Billy has the address, which is based off the public key, and he has the private key. He's keeping the private key private, but he has it at this point. Then here, when he goes to spend it, when he goes to send it to Kilgore, he basically shows proof to the network that he has the private key. He doesn't
in his possession.
Yeah, he doesn't disclose the private key. He doesn't say this is the private key. He signs a transaction with the private key, just like we talked about how you could sign a file to prove that you were the creator of that file. You have the private key. Someone with the public key can verify it. Same thing. Billy can sign the transaction and say, here's the result of me signing it. You can check my work and see that it's actually me.
And how do they check his work? Well, they see his public key. They see his address. So the network has both pieces of information in order to verify that it was really him. So for the detail-oriented, what Billy is actually doing, because the public key is not exactly the address, what he does when he presents his digital signature, he also presents the real public key corresponding to the address. So that right there is enough information for the miners to verify, hey, this is the real public key, And this is a real digital signature generated based on the address from which Billy is sending this Bitcoin.
Okay, so it's a lot of detail. All that really matters, Billy has a private key. He uses that to sign the transaction and prove that it's his money to spend, his address that he owns. So on this slide, we're showing that Kilgore, which is the pink here, now has ownership over those 3 Bitcoin that were sent from Billy. Now, Kilgore's wallet app generated some private key corresponding to this address. So whenever Kilgore wants to spend that, he has to produce the private key and sign. So he doesn't show everyone the private key, but he uses it to sign the transaction to prove that he owns it. And he also presents the public key to show, hey, check my work with this public key. The only way that this would work is if I signed it with the corresponding private key. Check my work.
So let's step back into the real world and talk about checks and how this would relate to actually writing a handwritten check. So here is my artistic rendition in Keynote of a check. From Billy Pilgrim to Kilgore Trout for $152. And what information is here? At the top left is Billy Pilgrim's name, and this is because the check was issued by his bank. It's it's his letterhead. The destination in the to field is Kilgore Trout. So that's for the bank to see, okay, this check, this amount is destined from Billy Pilgrim to Kilgore. And then the last most important piece of information is that Billy Pilgrim has sanctioned the check by signing it. And the thinking is only Billy Pilgrim can actually handwrite his signature. Yeah. Maybe someone could forge it, but if you looked close after the fact, if Billy were to contest it, they would be able to see that this wasn't the real signature.
Yeah, and this analogy doesn't hold up that well when you consider that it's not that hard to forge a signature, honestly, in the real world. But imagine the idea of signatures. It's the same idea. It's supposed to prove your identity. The thought process behind having you sign a check is that only you could sign that check. Only you can write your signature. So you can see here that this is what Kevin's talking about. The signature that Billy creates is based off of, or it includes the address, his address that he's sending from, the to address, Kilgore's address, the amount that he's sending, then he signs that whole thing with the private key, which again, the only way he could do that is if he had the correct private key. He produces the public key so people can check his work. Miners can verify that it's correct.
And this is why Bitcoin is valuable, is because people are confident that you cannot forge a signature, you cannot hack the system. And when you own Bitcoin, it can't be stolen.
Well, and when you own Bitcoin, what do you actually own, Kevin?
You don't own anything physical, you just own the private keys associated with addresses that contain unspent Bitcoin.
Right. So returning to this diagram, Billy sent Kilgore 3 Bitcoin. So now let's say that Kilgore wants to send those 3 Bitcoin on to Montana, which is the greenish color here. So it's the same idea. Kilgore has to then provide a signature that takes the address that contains 3 Bitcoin, the address that he is sending the Bitcoin to, along with the amount that he's sending, and he signs all of that to prove that he owns it. And then Montana takes ownership of that. Montana's address has a corresponding private key that she keeps. And this is a chain that could keep going on as long as somebody keeps trying to spend the Bitcoin.
So returning to our analogy, envelopes, drop boxes, this pink drop box above Kilgore's address corresponds to the entire transaction of Billy's address, Billy's signature, and then Kilgore's address. And then the next one, this teal, cyan one, is Kilgore's address, Kilgore's signature, and Montana's address.
Yeah, so these are the things that would be added to the blockchain, in the transactions. So this is a single transaction where on the blockchain we can see here's the from address, here's the to address, and we can also see the signature that was provided to prove ownership of the original Bitcoin in this address. Same thing here, from, to, and the signature. So just to illustrate what we're talking about, if we take a look back on the Blockchain Explorer, or one of the various apps to look at the blockchain, we're looking at I'm not even going to read it. Some block number, bunch of transactions. If we look at each individual transaction, we can see the addresses, but above it, you can actually see this hash of the transaction.
And that's just a unique identifier of the transaction.
So if we click on this, it takes us to a page where we can actually see more information. And the things that we care about, other than the input address and the originator, the from address and the to address and the amount, you scroll down, there's this thing here. It's called the script sig. We're not really going to go into too much detail, but this right here,
that's a signature?
This is a signature that whoever owned this address had to provide the private key to generate. They had to say, all right, here's the result of me signing the transaction. Here's the signature. And in order for you to check that, because they could just say that that's the signature, but in order for it to make sense, they also have to provide the public key, which is right here.
Yeah, so that public key, we talked about how the address is actually the hash of a public key, and we use them synonymously. That's the real public key right there.
Yeah, so I know it's confusing, but this is just if you want to take a look. This data is here. You do have to click on the actual transaction to view it. It's not just on the regular block page that lists all transactions. But again, to spend this, the person who had this address had to use their private key to sign the transaction. That's what we see here. And here's a public key they provide as evidence, as a way to check their work. So the last thing that we'll do here is show you that there's this chain of Bitcoin that goes back to, we don't know how many addresses. I mean, technically, this could be the place where this Bitcoin originated, but most likely, if we click on this address,
it came from somewhere.
It came from somewhere else. So if we scroll down, we can see on this address, so this is the outgoing, right?
That's the transaction we were just looking at on top.
And then here is where it came from, right?
Yeah. Click that guy. And now we're back at the address that it came from. Scroll down.
We can do the same thing.
And we can keep going back in time, back and back and back. So what's that look like? Well, we made a slide.
Yeah.
This is a rough diagram of what the blockchain looks like, or what the sequence of transactions look like. It's just the transfer of ownership of Bitcoin from address to address.
Yeah.
And that has some implications in terms of the anonymity and privacy of Bitcoin. Remember that everything on the blockchain is completely public. You can keep the ownership of your address private, and we'll talk about anonymity in a later section. And that means that if we take any individual transaction, for example, this blue one, we can see the sequence of addresses that it came from.
So to wrap all of that up, in each one of these transactions, the person who owned an address had to provide the corresponding private key, keep it secret still, but sign the transaction to prove that they owned it, and also provide the public key so other people could verify that. And then that happened again here. So this person could send the Bitcoin to this person. And if this person in the blue envelope wants to send it on to someone else, they would have to sign the transaction themselves to prove that they own it. All right, welcome back. So one thing that we've kind of skimmed over is the fact that not all transactions are one-to-one, meaning one address in the from column to one address in the to column. In fact, most aren't, and we'll talk about why in this video. So you probably have noticed this if you've watched any of the videos where we're looking at the blockchain. If we scroll down on just any given block, there are many transactions that are one address going to two addresses. Or here's one that is, what is that, five addresses to two? 1 to 2, 1 to 3, looks like. So it's not always one-to-one. In fact, one-to-one is really not that common. But all that we want to show in this case is that there's all different sizes, all different flavors of transactions, whether it's 1 or 5 or 10 addresses on the
50.
from side or on the to side.
So here we have the simplest transaction, and that's just moving Bitcoin from one place to another. And suppose the source address has 2, the destination has 2.
So we're not losing any Bitcoin, or we're not having any leftover Bitcoin.
Nope. This is a pretty simple transaction.
Okay.
So the next scenario would be, suppose you need to send 5 Bitcoin to somebody, but you have multiple addresses and none of them have 5 Bitcoin. You don't have enough. So what you actually do is you assemble a list of addresses that contain as a sum enough to send the amount that you want to send to your destination.
For example, here on the blockchain, we just found one. In this case, it's actually 3 inputs, but all of them, if you look, they're tiny amounts, and there's only one output. So these 3 were added together to meet this, whatever this is, 0.04925 Bitcoin, which are sent to this address.
Now the use there is that you don't need to have exactly the right change to send to somebody.
So most likely this is someone who it's really unlikely that they would be paying for something and they just happen to have the exact amount of these tiny little pieces of Bitcoin. They probably were just combining a bunch of small amounts together to have one address that had a little bit more.
So as we alluded while we were looking at the Block Explorer, what about the word change? What about when you need a refund, when you want just part of an address to be sent to somebody? So suppose we have 5 Bitcoin and we want to send 3 to someone else. there's no way to cut an address in half. You can't just send part of the Bitcoin in an address to somebody. Once you use the Bitcoin in an address, it's permanently gone. So an unspent transaction output, which is really what we're talking about here, the Bitcoin in an address, once it's used in a transaction, it's gone. So in order to get change, if we wanted to send 3 to our destination, we would need 2 back. And how would we do that? We wouldn't actually keep 2 in the source address. What we end up doing, what our wallet app will do for us, is we create a new address.
Yeah. So there's the first address that we're sending the 3 Bitcoin to, and then the leftover we send to a new address that's created for us with a new private key that corresponds to it. And so we still have possession over this. We don't have possession over this. Hence the little shiny part there.
Oh, I love these effects.
Okay. So if we hunt around on here, I'm sure we can find, here we go. Here's an example. So this address had 101.38869 Bitcoin in it.
We see 2 output addresses here. One of them has 0.05 Bitcoin and one of them has 101 Bitcoin, that's $1 million. What's important to note here is that we don't know which one is change for the sender and we don't know which one is actually pointed at the destination. It's hard to say. Do you think they were sending 0.05 to somebody and they kept 101 in change? Or do you think they were sending 101 and they just needed 0.05 in change? Because these addresses are anonymous, we don't know. But what is indicated here, what's interesting about this block explorer is it shows whether or not the Bitcoin associated with that address is spent. So the bottom one, the 101 Bitcoin, the $1 million or so that just moved, has already been moved somewhere else. The top half, the 0.05, hasn't been spent. It's still sitting in the address, starting at 154YEJ. And then the bottom half, the 101, has already been moved. And it actually looks right below it like it's moved immediately. So the transaction right below, 17AGW, or is that 2 V's, is moved to a new place. And then they have 0.11 unspent and 101 spent.
Right. But remember, when it says spent, it doesn't mean that because the way addresses work, it could be tiny, tiny fractions of a Bitcoin being moved, but that address is considered done. So spent doesn't mean somebody sent $1 million in a transaction. It means that somebody sent any number and then the leftover was sent to another address, like we've been talking about. So it is confusing. Technically, I guess it does mean that it's spent. It is moved around, but it's just spent to another address that you still own.
Yeah, so those addresses are empty now.